In this segment, we'll begin a discussion of Markov chains. Now we'll be dealing with finite probability spaces, so there's no conceptual difficulty in using the power set of the sample space to define the relevant sigma algebra. And this is what we'll do. We'll consider finite state Markov chains, and the defining feature of these is that the probability of any particular state arising in period n depends only on the state that occurred in the previous period, and not on any longer history of the process. We'll discuss higher order transitions, so this is the likelihood of transitioning from a state I to a state j in some number of periods n. We'll see that for any initial distribution over states, a Markov chain can be described as a dynamical system in the space of distributions. And we'll end the segment by thinking about a rest point of this dynamical system, which is referred to as an invariant distribution. So consider a probability space omega sp, where omega is a sample space, s is a sigma algebra, and p is a probability measure. Now if omega is finite, we can let the sigma algebra be the power set of omega, and this is often left implicit, so the pair omega p is referred to as a finite probability space. Now any subset of omega, which is an element of the power set, is referred to as an event, and the image of A under P is the probability that the event A occurs. Two events A and B are said to be independent if the probability of their intersection is the product of the probabilities of the individual events. Now if A and B are two events and the probability of B is positive, the conditional probability of A given B is defined as shown on the slide. And putting these two formulas together, we see that if A and B are independent events, then the probability of A conditional on B is just the probability of A. Now consider a collection of sets B1 to Bm. This is referred to as a partition of omega if each of these sets is a subset of omega, if they're pairwise disjoint, and if their union is equal to omega. And for any subset A of omega and any partition B1 to Bm, the probability of the event A can be expressed as the probability of A conditional on Bi times the probability of Bi summed across all sets in the partition. Now we'll define random variables. A random variable x is a function from omega to some subset of the real numbers, and the probability that the random variable takes a particular value x is simply the probability of the set of states omega whose image under the random variable is equal to x. The expectation of x is defined as the value of x at sample point omega times the probability of that sample point summed across all points in the sample space. Now we'll define finite state Markov chains. So consider a finite set S. This will be our set of states. For each pair of states ij in S, there exists some non-negative number pij, which we'll interpret as a transition probability, giving us the likelihood of going to state j if one is initially at state I. And the sum of these transition probabilities across all states j must equal 1. Now let x0, x1 and so on be a sequence of random variables with ranges in S. The subscripts here we'll interpret as periods. So x0 is the initial period, x1 is the value of the random variable in the first period, and so on. Now this sequence of random variables is referred to as a Markov chain if the probability that xn plus 1 equals j conditional on some history is equal to the probability that xn plus 1 equals j conditional simply on the last element of that history. In other words, on the value of the state in period n. And this must be true for every n and for every history that arises with positive probability. Now as already noted, the set S is called the state space, and the numbers pij are the transition probabilities. The random variable xn is interpreted as the state in period n. And we'll assume throughout our discussion of Markov chains that the transition probabilities don't vary with n. Now in words, the Markov property says simply that the probability that the state in period n plus 1 is equal to j depends only on the state in period n and not on any prior history. We say that a matrix is stochastic if it has non-negative entries and rows that sum to 1. And it's clear that the transition matrix P is stochastic because the sum of the probabilities Pij summing across all states j is equal to 1. Now if you have some initial probabilities over states pi0 exogenously given, then the transition matrix P implies a distribution over period 1 states, and hence period 2 states, and so on for all periods. Now before we look at this dynamical system in more detail, let's take an example. Consider two boxes, each of which contains R balls, and these balls can be white or black, half of them are white and half black. The random variable xn denotes the number of white balls in the first container in period n. And in each period, one ball is drawn from each box, and these two are exchanged. Now let's look at the transition probabilities. So suppose that we have I white balls in the first container in some period, and we want to consider the likelihood of transitioning to state j in one period. Now the probability that you'll go from state I to state I minus 1 is shown on the slide. This is just the probability that you'll draw a white ball from the first container and a black ball from the second container and switch them. And similarly, we can obtain the probability of going from state I to state I plus 1, and the probability of remaining in state I, and Pij is equal to 0 otherwise. Now this is true for I between 1 and r minus 1, and you can easily verify that if you start from a boundary, you'll move away from the boundary with probability 1. Now what you see here is a sample path for this process when r is equal to 4, so you have 5 possible states. The initial state is 0, and the path taken by this process for the first 100 periods is simulated. We want to think about the frequency distribution that's generated from sample paths like this. Now here you see some frequency distributions for a sample path truncated at different lengths and starting from the state 0. And you see that after 10 periods, the probability is skewed towards 0, but starts to look more symmetric as you look at longer sample paths. And by the time the number of periods is equal to 1,000 on the bottom right, you're approaching a symmetric distribution over these 5 states. Now here's a different set of frequency distributions, starting from the state 4, and you can see that for a short sample path these are skewed towards the right, but seem to be converging to the same symmetric distribution as we had from a different initial condition. Now suppose that we have a sequence of random variables xn, which satisfy our conditions for a Markov chain. The transition matrix is P, and the initial probabilities over states is pi 0. Let pi n denote the probability over states in period n, given that the initial state is drawn from pi 0. Now note that the probability of state j under pi n is given by the formula shown on the slide. This is just the probability that j will be reached from state I in the previous period, summing across all possible states I. And so the transition matrix P defines a linear difference equation system in the space of probability distributions over states. And given the initial distribution pi 0, pi n can be expressed as the product of pi 0 and the nth power of P. Let capital Pi denote the set of all probability distributions over states, and note that pi is a convex and compact subset of Rm. This will allow us to use Brouwer's fixed point theorem to establish the existence of a rest point of the dynamics. Now we need to verify that if you start off with a point in this unit simplex, then the image of that point also lies in the unit simplex. And this can be seen easily based on the fact that P is a stochastic matrix. And the proof is just mechanical, so pi n of j is just the probability of transitioning to j from state I summed across all states I, and summing these probabilities across all j gives us the expression shown. Now we can factor out the term that doesn't depend on j, and note that both of the terms in the product here are equal to 1, because pi n minus 1 is a probability distribution, and P is a stochastic matrix. So we see that pi n is an element of the unit simplex, provided that pi n minus 1 is an element of the unit simplex. In other words, the unit simplex is invariant under the dynamics. Now pi is the set of distributions on S, and as we think about convergence, we need to think about the distance between two distributions. So for any two distributions pi and pi prime in the simplex, we define the distance using the metric d1, which is just the sum of the component-wise distances between pi and pi prime. Now with this metric, the simplex is a metric space, and the pair pi p is a dynamical system. And any distribution pi star that's a rest point of this dynamical system is said to be a stationary or invariant distribution. And we'll be interested in existence, uniqueness, and stability of these. Now we'll begin by showing that the system is described by a non-expansive map. So recall the definition of this. We need to show that the distance between the images of 2 points, pi and pi prime, is less than or equal to the distance between the points themselves. Again, the proof is mechanical. So here's the definition of distance between two distributions pi and pi prime. Now the distance between their images, pi p and pi prime p, is as shown on the slide by definition. Now use the fact that the jth element of pi p is just the product of pi with the jth column of the transition matrix to get the expression shown on the slide. Then collect terms to simplify. And then note that if we take the sum of the absolute values instead of the absolute value of the sum, we get the weak inequality shown here. And now factor out the terms that don't depend on j to get the expression shown. Use the fact that P is a stochastic matrix so the second summation is equal to 1, and we see that the expression we've obtained is just the distance between pi and pi prime. So we've shown that the distance between the images of pi and pi prime is less than or equal to the distance between the 2 points themselves, which is what defines a non-expansive map. Now, as we've seen, the unit simplex is a compact and convex subset of Rm. The map p pi is clearly a continuous self-map on pi, and hence by Brouwer's theorem the system has a fixed point. And this is exactly what we mean by an invariant distribution, so we've shown that every finite state Markov chain has an invariant distribution. This deals with the existence question, and we'll address uniqueness and stability in the next segment.